Hello, this is Dr. Liu, and this video is about rounding, significant figures, and scientific notation. So we all know about rounding, and rounding should be pretty simple. And then I want to make it a little more complicated because I want you to think about rounding. So let's say we want to round a number 3.14. Okay, so that's pi. Okay, so let's round to the nearest 100th right here. All right, so we have a 4 there, and the next digit is a 1. So numbers 0, 1, 2, 3, and 4, they basically they just drop. So we have 3.14. And let's round to a thousandth. Round to 1,000. Okay. Okay, so now this time we're looking at this digit 10,000 to see if we should carry or we should drop. But now we have a 5. So if I remember right, 5 through 9 we should carry. So we have 3.1142. All right. So we can keep doing this exercise because pi has a lot of digits. It doesn't repeat itself. All right. So it's going to be fun trying to round to the next to the nearest 1,000 billionth. Right. So this is just a point. We see two different outcomes of rounding. One of this is you drop, right? You dropped the 1 to just to maintain the 4, and this is another situation where you carry, right? You round up, right? This is round down, this is round up. You carried, so the 5 turns into another 1, right? So the scenarios here drop. If you have a 0, 1, 2, 3, and 4. But wait a second, 0 is not part of it because 0 turns into 0. There's no dropping. Dropping means you were more than you were less, right? After you dropped. So only 1, 2, 3, 4 actually we drop. And then if we carry, let's write this better. Where we round up, we have 5, 6, 7, 8, and 9. So now we see that we carry more often than we drop if we assume that the digit we're looking at is randomly showing up as any one of the 10 digits. Here's also a no change. It's 0. All right, so what this means is no change is kind of fair, right? It doesn't favor either dropping or carrying, but now we have more carrying cases than we have dropping cases. So let's remove that 5. We have to make it fair so that the 5 either drops or get carried. So how do you decide which way? Well, you can say that to make even. So what I meant by even is, see, I'm actually rounding here 3.1415, right? It was a 1.5. And by carrying the 5, I made that 1 an odd number into a 2 even number. So this is convenient if you decide to divide this by 2, for example, and you don't spit out an extra digit just by dividing an odd number by a 2, right? So you're looking at the number, the 5, that you're going to either drop or carry, and the effect of that must make the next digit. You round to 1,000, so it must make the 1,000th digit an even number, and this is what we call it rounded to even. So this is called round to even. Okay, so this is an extension to what we are already familiar with. 5 through 9 we carry, and 1 through 4 we drop. Right? This is a bit more well, even or fair around all the digits. Okay, so now let's move on to significant figures. So why are we rounding anyway? Is it just to save some spaces when we're writing numbers? Of course, we don't want to drag around all these digits that are not necessary. So what do I mean by unnecessary? Well, that means it is not significant. For example, if you're making a measurement with a ruler, I have a ruler in my hand, and you're trying to measure the size of something. I have a let's see. I have my glasses, so I just want to measure the length of one of the metal legs. So I take my ruler to it, and I can read. I think I can read as finely as maybe a millimeter, but not more accurately. So if I want to write down the measurement of my glasses, it's just going to be in millimeters, such as this. Let's do sig figs. So 15.1 centimeters of length. This is because I don't have a more accurate device to measure the length, and also I have trouble determining which part is the starting point of this leg because of the little curvature next to the frame. So anyway, there are limitations to how many digits you can comfortably quote as a result of a measurement, and that is why there are significant figures. Only those that you can comfortably present are significant, and those you cannot, they're not significant. So for this number, we assume that we have 3 sig figs. It's easy to understand this because we presented 3 digits, right? So what if I actually measured more accurately? I was using a caliper, so I was able to produce another digit, and that happened to be this, for example, 15.12 centimeters, right? So this is assume we have a 4 sig fig, right? What if I have 15.1 exact, but I was using a caliper? So if I just wrote 15.1, that means I was using maybe a less accurate device, maybe a ruler, right? So how do I say that I have a digit here, which happens to be one of these digits, a 0, and it is significant? So I have to just explicitly put a 0 here. So this assumes a 4 sig fig. Okay, so if you attach these trailing zeros, you specifically wrote them out, it means they are significant. And okay, so let's do something else. Let's convert the unit into meters. Say I have a net number that is 0.151 meters. Okay, so how many sig figs? So we're still assuming, and we actually have 3 sig figs. And what we just observed is this leading 0 is not significant. So they're not sig figs. And I'll keep writing. I'll just write this number here. This one is 0.1512 meters. Apparently still is 4 sig figs. And if I do a 0.1510, still 4 sig figs. So what we conclude here is the trailing zeros are significant. Although not all mathematical tools recognize these trailing zeros as significant, we do. So if you write them down with a 0, that just means you made a measurement. It's one of those 10 digits that's going to show up as a lost digit, and it just happens to be 0, right? It's one of the 10 chances. So this is this. And what if we let's do this. We convert this number into not millimeters, into micrometers. Microns are much smaller. So 1 meter is a million microns, a million micrometers. So let's try to convert this correctly by multiplying this number by 1,000, 1, 2, 3, another 1,000, 1, 2, 3. So I have 151,000. I can put a comma here. Microns. So this is mu. Okay. So can we still assume how many digits are significant? 3 or 6? Because of these trailing zeros, we have to write because the number is so big in this unit, right? That's really a headache. You have to maybe make a mark, maybe just try to underscore these digits to say these are significant, but that underscoring is not universally understood. So let's also convert this into microns. So 151,200. And how many sig figs? 4, like we had before. Or is that 6, as you assume all these trailing zeros are significant? What about this? This will be the most confusing. 151,000. And is that 3, just like these? Or 4, because somehow you knew this was actually significant. How did you know it before you even see this number, right? If you are only presented this number, how do you know that one of the zeros is significant? Or we just assume every digit is significant, right? So that comes to a point that we cannot really just make assumptions of sig figs. If we have a decimal place, we can make these unambiguous assumptions of sig figs, right? We have a decimal place. If we don't have a decimal place like this, we're lost. So what we need to do in order to express any quantity, large or small, in the right amount of significant figures is, number one is we need a decimal place. So we know that these numbers are significant. The zeros included are significant. And number two, we need to describe big and small numbers just the same. So that would require a scientific notation. So for scientific notation, this number is turned into a 1.51 times. I usually do this as times because I use x. X looks like a times, right? So I use star for multiplication. 10 to the, well, let's move 1, 2, 3, 4, 5 places. So we move the decimal, which was here at the end of the 0, 5 places to reach this place. So there's 10 to the 5th power micrometers. Oh, I forgot microns here. Micron here. All right, so now what we just accomplished was we expressed the numerical value of 151,000, correct. And we also expressed this with a decimal place right here. We have an easy way to assume there are 3, right? 3 sig figs. Because this is clear, 3 sig figs. What about if I have 4 sig figs? So this is 1.51, 12 times 10 to the 5th power micron. So this is no longer ambiguous. We have 4 sig figs. Right, so these are all significant. What about this? I actually have 4 sig figs and the last digit happens to be 0. Oh, that's easy. 1.510, right? See that? The trailing zeros are significant, but those, I don't really know which one is significant or which ones are, right? So if we have a decimal place, we know everything trailing are significant, right? So this 10 to the 5th power again, micrometers. So we have 4 sig figs. So this is what we need this for. We need this for very big numbers. We can also use that for very small numbers. But what this the scientific notation gives us is this decimal place, so that any number, all these numbers, we can say all these digits. And let's rewrite that. all these are sig figs. So this frees us from having to guess all these trading zeros, are any of them significant or not. Thank you.